The next presentation will be from Athanasios, and
Yes.
Athanasios, can you connect? Share your screen?
Yes.
Okay, good.
Can you see my screen?
Yes, perfect. And we can hear you and we can see your screen.
Perfect.
So the topic of this presentation is evaluating deep reinforcement learning algorithms for quadrupedal slope handling. So another quadruped data. So you can proceed.
Yes. Hello, I am Athanasios Mastrogeorgiou, and I'm going to present an evaluation framework we developed here in the Control System Lab in Athens with Yehia Elbahrawy in order to test the different reinforcement learning algorithms for the task of quadrupedal slope handling. The basic idea is for this research work is that reinforcement learning is rapidly advancing nowadays, and there are a lot of different approaches using RL algorithms that are able to map sensory inputs to low-level actions and produce stable locomotion on slopes. We wanted to evaluate and choose the most suitable algorithm for this task. So, the contents of this presentation are the simulation framework, the top trajectory, the chosen RL algorithms for evaluation and the reason behind this choice, the steps of the training procedure, and the summary of the results. So, first of all, let me explain a bit about the Laelaps quadruped and how we model it. The two pictures on the left and in the middle is the current version of Laelaps Robot on the treadmill in CSL in Athens, and on the right you can see the Laelaps Robot in Gazebo. So first, we build a detailed description of the leg. We modeled the transmission arm, the femur, the tibia, and the foot. Also, we modeled the linear spring between the tibia and the foot, and the cable for the transmission of the torque to the knee joint. Next, we created the surroundings of the environment. All the bodies are rigid and undeformable, and we utilized the open dynamics engine from Gazebo. Cross control package was used for low-level PD control for the 8 actuated joints at the hip and the knee of the Laelaps leg. Then we used OpenAI Gym toolkit and connected it with Gazebo. Gym is a toolkit for developing and comparing reinforcement learning algorithms. It offers a collection of test cases. There we create a new environment which gets all the sensor readings from Gazebo simulator. The difference between the implemented environments in Gym and our new environment is that all sensor readings are from Gazebo, and we are using the Open Dynamics engine that Gazebo provides. The basic setup for learning was the Laelaps quadruped and a RAM of 10 degrees. This setup is similar to the treadmill robot setup in Athens in the Control System Lab. We built this environment because we wanted to transfer the learned policies in the real robot in the future, so the environment in simulation is similar to the environment in the lab. In order to reduce training time, we use trajectory planning on top level. Specifically, instead of seeing the whole locomotion problem as a black box, we try to deal with it using RL. We made a few choices based on our experience on legged robots. As a result, we chose parameters such as the stride length and the foot clearance from the ground, and we left for the algorithm to learn the points to apply the top trajectories. Concerning the trajectory planning, we applied the semi-like trajectory that you can see on the right, with the difference that we can define the swing period and the stance period of every cycle. Concerning the taxonomy of the RL algorithms, basing on the environment interaction, they can be divided in model-based and model-free. Basing on the action estimation, they can be divided in value-based, policy-based, and combined methods. So, in this general schema of the RL algorithms, if we follow the red and then the black track, we have the model-free option, where the agent is interacting with the environment and is learning the controller directly from experience. If we follow the green and then the black track, we have the model-based option, where an accurate model of the foot and the environment is required, of the robot and the environment is required in order to learn the controller. We focused on the model-free category because it's often hard to model complex environment, especially in legged robots. More accurate environments should be stochastic, and the transition dynamics are usually not known. Now regarding other RL characteristics, the algorithm can be categorized in the RL algorithm can be categorized in on policy or off policy concerning the learning mechanism, deterministic or stochastic policy concerning the policy function to be learned, continuous, discrete or combined concerning the action space that the algorithm can handle. So in this work we applied three algorithms. We focused on the model-free ones and covered all options of them. That is on policy, off policy, stochastic, deterministic policy, and of course all algorithms could handle continuous action spaces because the action space of our work is also continuous. Here we have summarized the training procedure. It involved 5 steps. First, the Gazebo environment, where every algorithm could take the observation from. Second, the DPRL part, where the algorithm is producing the center point around which the trajectory planned in the next part in 3 will produce the semi-elliptic-like trajectories. 4, the inverse kinematics part, where every point in the trajectory is translated to the corresponding joint angles. And last 5, a PD controller produces the torques to be applied to the motors. We have to mention that the reward function that we used promotes forward motion and parallelized drifting motion. Of course, we have some termination criteria. If the robot falls off or if the robot drifts too much, we have defined the state space and the action space. The action space is the center of the semi-elliptic trajectories, which is the output of the deep reinforcement learning algorithm. Now, concerning our results, every algorithm has an optimizer inside. Every DPRL algorithm includes an optimizer in order to minimize the cost function during the training procedure. Since there are a lot of different optimizers available, we want to test them and see which one converges faster and is more stable. Adam was the best option, and this is also the main reason that makes Adam the most widely used optimization algorithm. More, as you can see on the right figure, some algorithms such as SAC include parameters that require tuning, for example, the entropy term of SAC. This framework enabled us to have an insight on how sensitive was SAC concerning the entropy term. So for low values of entropy, close to 5 or 10, the mean reward remained very low and the algorithm could not learn the policy. For values of entropy close to 300, the algorithm converged very fast, and after 7 or 8,000 steps, it reached a mean reward of more than 2.5, close to 3, which is close to the maximum reward. After tuning all algorithms, we tuned SAC, we tuned DDPG, we tuned PPO, the 3 algorithms we used. After tuning all of them, we wanted to study how stable and sample efficient are they. Again, SAC was the most sample efficient one. Every training experiment converged quickly after 8,000 steps to the maximum reward and stayed there. In turn, we tested the learning policies to see how the robot behaved with these learning policies. And they produced, as we expected, stable motions, and the body roll and yaw angles were bounded. This is shown in the diagram on the right. Next, generalization is very important in DPRL because we want the learned policies to be able to handle different scenarios and not only the ones that the robot was trained at. Again, SAC was able to reach the top of the variant relation RAM, although it was not trained in this specific task. You can see on the video on the left that although the robot was trained at the 10-degree ramp, it could handle a different RAM of variant inclination that starts from 10 degrees, goes to 8 degrees, and then to 15 degrees. And on the right, we have summarized the policies and how they could handle this varying relation RAM. SAC arrived at the top, DDPG arrived close to the top but not as SAC, and PPO was the worst at generalization. Last, The major outcome of this work was the fact that we switched from DDPG to SAC for our main deep RL algorithm. For the control of Laelaps Robot, since it was more stable, more sample efficient, it trained faster and generalizes better. Here in this slide, we have summarized all of our work. What you can see on the left is going to be presented in IROS. We started without DeepRL, where the robot could not handle slopes. With DTPG, we were able to handle slopes of 10 and more degrees, but training time took 3-4 hours. And with SAC, everything was improved because it needed less time to train. It was generalizing better. So we switched to SAC as a deep RL algorithm for the control of the Laelaps robot. Here I have some indicative references. Our paper was based on previous papers from the Control System Lab in Athens, and some of our works are going to be presented in future conferences. So thank you, and if you have any questions, please ask.
So thank you very much, Athanasios. Anyone has any question? Maybe I can ask one question.
Yes.
Regarding the Gazebo simulation, so I wanted to ask you, do you have any idea how this simulation results can be used in the practice? I know that the reinforcement learning training for the simulation, most of the cases does not map to the real world robot itself. And the other question is that how long it takes for the Gazebo to manage to do all those sample training cycles, because reinforcement learning would need a lot. It would be a good idea if you give us some idea of how long it takes for the one training.
Yes. First of all, we tried to. We haven't tested it on Laelaps Robot yet. In fact, this is an ongoing work that we are trying to do now. But the environment we have created has all the torque limits of the real robot, has the same coefficient of friction between the ramp and the robot leg, so the robot foot. So we tried to make it as realistic as possible in order to be able to be applied on the real robot in the future months. So the answer is that we haven't tested it yet, but we think that we are close. And what was the second question? How much time? Yes. Yes. For us, we're going to present in IROS for DTPG. It took about 3, if I remember correctly, 3 or 4 hours for the robot to train and to learn to go up, down, or down, because we have also trained the robot to go on negative slopes. And for PPO, as you can see on the diagram close to the end, what I want to say is that for every algorithm, it needs different amount, different time. So as you can see on this diagram on the left, PPO needs 20,000 steps. SAC converts very fast after about 8,000 steps, and DDPG also converts fast, but with a lower mean reward. So for SAC and DDPG, it's about 3-4 hours, something like this. For PPO is a lot more, 3 times more.
Athanasios, one question. You did not simulate the actuator dynamics inside.
We simulated the maximum velocity, the maximum torque, and the inertias. So we simulated we simulated part of the dynamics, which is the maximum torque, minimum torque, maximum velocity, and rotor inertia.
Ah, good. Cool. Okay. Thank you very much.
In the paper, there's a Okay, thank you.